Hey everybody. So following from that last video, let's continue our discussion about conservation of momentum. So during a collision, momentum is constant or conserved. So we can say the momentum, let's say initially before a collision, initial, is the same as the momentum after a collision, final. So this is a good way to start. If you have problems involving collisions, you just set the momentum before the collision equal to the momentum after the collision. So for example, let's say I have a smooth surface and there's a block here going this way. Let me make up some numbers. So let's say it's 3 kilograms. And then there's a block here. And I'll just make up a number going this way. Okay, and then let's say this is 4 meters per second. This is 5 meters per second. Okay, what's the momentum for block 1? Let me pick coordinates. I'll say this is y and this is x. The momentum for this block is m1 v1. And right, it's so 3 kilograms times 4 meters per second, 12 kilogram meters per second. Is that right? The momentum is a vector. What I wrote is a scalar. Here. Now that's a vector. How about the momentum for block 2? 5 times 2, 10 kilogram meters per second. But it's a vector. Right, it's going in the negative I direction. Okay, so now let's use this in a problem. Let me just make up a problem. So let's say this is the situation before the collision, and then they collide, and then let's say they bounce off of each other and then go flying, let's say this way. So this is before the collision, this is during the collision, and then this is after the collision. I'll just have the picture like this, before and after. Okay, and then let me just make up numbers here. So how about 2, and what is this? So this is still the 3 kilograms and 2 kilograms. Okay, so this is before the collision. After the collision, let's say you measure this, but then you want to compute this, the velocity of block 2 after the collision. Okay, so how do you do that? So we said the momentum initially equals the momentum final. And then this is all in the x direction, so this is, I'll just write the x component of everything. Okay, so initially, m1, v1 initial. So that's for this. This also has momentum. m2, v2 initial. So we're computing the momentum of this system. Okay, and then after the collision, this system here. So the momentum of this, m1, v1 final, m2, v2 final. And our unknown is this final here. All right, so just move this on that side. Plus m2, v2 initial, divided everything, and then divide everything by m2. Over m2, over m2. There we go. Okay. But let's be careful when we plug in numbers here. m1 over m2, so that's 3 over 2. Okay. v1 initial, 4, positive 4. v minus v1 final. That is negative 2. So 4 minus negative 2. right? Just be careful. Plus V2 initial, negative 5. Okay, so what do we got here? So this is 6. So 9 minus 5 is 4. Okay, so that's our answer. 4. 4. Oh. 4. Okay, and then be careful to not mix up momentum and energy. These are different things. For example, how much energy in the system before the collision? How much energy? So kinetic energy, and then let's say the datum is here. So the potential energy is 0. And then after the collision, everything's at the same datum. So really, we're just concerned about the kinetic energy. Right, so the kinetic energy, let me just jot it here on the side. Kinetic energy initial, 1/2 mv squared. So 3, 4 squared. And then this one, 1/2 mv squared. Okay, so that's 16 over 8, so 24, 25 plus 25. So 24 plus 25, 49. Okay, so 49 joules before the collision. How about after the collision? Final. So, okay, so for this one, 1/2 mv squared and 1/2 mv squared. Okay, so that's 4 over 2 times 3 is 6. 16. Okay, 6 plus 16. 22. Okay, so 49 joules before the collision, 22 joules after the collision. So momentum was conserved, but energy was not. We lost a bunch of energy, actually, right? So be careful not to mix the two. So that brings us to a discussion of there are different types of collisions. So when there's a collision where energy is lost, like this, that's called an inelastic collision. Okay, so for inelastic, momentum is conserved, but energy is lost. An elastic collision, energy is conserved. So this is like a special case situation where energy and momentum are both conserved. Okay, and then there's another situation, kind of special type of inelastic collision called perfectly inelastic. That's the case where it's like the maximum energy lost, the maximum possible amount of energy loss, and that's practically when two objects collide and they stick together. Stuck together. So for example, let's say this same situation, here let me just copy this. Okay, so let's say same initial condition here, but now the two objects stick together. Okay, how fast are they going after the collision? I'm not sure which way they're going to be going, but I know momentum is conserved, so initial, final. So initial, m1 v1 initial plus m2 v2 initial equals the two of them stuck together, m1 plus m2 going, I'm not sure which way, some final. Okay, so solve for that final. Just move this in the denominator. M1 V1 initial plus M2 V2 initial over M1 plus M2. Okay, so what numbers do we plug in? M1, 3, V1 initial. If I call this way positive, then that's positive, plus M2 V2 initial, so that would be negative, over M1 plus M2, 5 kilograms. Okay, and then just punch that. Okay, let's see. So 12 minus 10 is 2 5/5, 0.4. Okay, so we solve that. And then how much energy here? So the energy here was, how much was it? 49 joules. How about over here? Final, 1/2 mass, so the two stuck together, 5 kilograms, 0.4 squared equals 0.4 joules. So look how much energy was lost in this perfectly inelastic collision where the objects stuck together. Right? And this is in fact the most energy you could lose when they stick together. Okay. Let's save for another video elastic collisions. Okay, so I'll see you on that next video.